All right, good evening, everyone. Sorry for the delay there. We just ran into a few snags with the Zoom, but I appreciate you guys all bearing with us today and for joining us today. Really awesome to have you all here with us for the inaugural Blockchain Fundamentals webinar series. To give you all a little context in case you didn't know, normally this class is taught on UC Berkeley's campus, but due to COVID-19 and remote learning anyways, we decided to take advantage of this opportunity and open up to the public. And so we're really, really excited to have you with us for this series. I'm going to go ahead and introduce myself in just a second, and then I'll introduce my partner, Andrew, here, or I'll let Andrew introduce himself. Before I dive into that, though, I do just want to say there's a lot of ways to get in touch with us throughout the series, and we highly encourage you guys and we highly encourage you guys to ask questions. So there's a Q&A box down at the bottom of your Zoom screen. I definitely recommend you asking questions there. We've also got staff helping to answer those questions. And then we've also got a chat. We're going to be sending a post-webinar feedback form probably tomorrow. And then, as Andrew mentioned, we're also going to be posting all of these recordings on YouTube. So in case you've got any friends or family that want to view this, it'll be accessible that way. And then we'll also talk about this in just a second as well, but we've also got a Facebook group. And so we definitely encourage you to join that Facebook group in order to continue the conversation even after the webinar ends. Now, without further ado, let's kick things off. Oops. So before we dive in, I just want to introduce myself really quickly. My name's Liam. I'm one of the co-presidents here at Blockchain at Berkeley. I joined Blockchain at Berkeley in January of 2018. And since then, I've also worked for Ripple for their university and spring teams. I'm one of the organizers for SF Blockchain Week, which is one of the largest blockchain conferences on the West Coast. And I'm currently at PayPal's blockchain research group. And today we're going to be going over just at a high level. We'll start off with some introductions and logistics, going over some of the ground rules for the webinar and what we're going to be covering throughout the series. Then we'll dive deep real quickly into what is Bitcoin. As I'm sure for those of you who aren't too familiar with blockchain, hopefully you at least know what Bitcoin is. And if you don't, we'll talk a little bit more there and the motivations behind Bitcoin. And then we'll talk about a lot of the principles that make up these blockchain ecosystems. So identity, how transactions work, what is a distributed ledger and why is it important, and how do we empower distributed ledgers through trustless consensus. To go over some quick introductions, we've got an awesome core staff for this series. And with that said, I'd like to pass it over to Andrew to give a little intro on himself.
Thanks, Liam. Yeah, so my name is Andrew. As you can tell by the slide, I'm part of the education department here at BAB. One of the things we do is put on what was previously the decal and what is now the webinar that you're viewing with us. I'll also be one of your webinar leads over the course of this entire series, which basically means that if you have any questions about, maybe you're not in the Facebook group anymore, maybe you missed the last lecture and you can't find the link, anything sort of administrative on a course level, I'm one of the people you can reach out to. You'll also probably see me posting a lot on the Facebook group, trying to answer questions and whatnot. So I should be pretty active. I'm sure everyone here will get to know me better.
Awesome. And yeah, like Andrew mentioned, we've got a really awesome core staff that's going to be helping throughout this entire series. And so definitely ask up those questions and give us feedback, as we want to make sure that it's catered well to all of you. To give a little bit of context on Blockchain at Berkeley, for those of you who aren't aware, Blockchain at Berkeley is a university-based organization that aims to drive innovation in the blockchain industry by building an ecosystem that empowers students as well as the general public to create an impact through practical education, consulting for enterprise companies, and conducting open source research. To give you a scope of where some of our members have gone on to, our members have founded the Berkeley Blockchain Accelerator. It's a really awesome accelerator. It's a joint venture between Blockchain at Berkeley, Berkeley Haas, and the College of Engineering. If any of you guys have blockchain startups, I highly, highly recommend you check it out, as it's and I'll talk a little bit more about it actually just in a couple slides. Some of our members also went on to co-author the Facebook Libra white paper, which many of you I'm sure are familiar with from all the news articles. Our members also went on to found and raise $20 million for Decrypt Capital, which is a VC based out of San Francisco. Myself and other Blockchain at Berkeley members, as well as alumni, have every year we host SF Blockchain Week, which has over 5,000 daily attendees. Really awesome event and the largest one on the West Coast, and I definitely recommend you check it out to continue your learning. And then our members also created an organization called Sheet 256, which is really awesome because it's promoting diversity in the blockchain space. To give a little bit more context on Blockchain at Berkeley as a whole, in addition to education, which our educational initiatives has reached over 160,000 students worldwide. But in addition to education, we also have consulting. And so our consulting team has built out proof of concepts for a wide range of Fortune 500 clients, in addition to contributing to blockchain protocols and developing dApps on top of protocols. And then as I mentioned, we've got the awesome Berkeley Blockchain Accelerator, which is the #1 university blockchain startup accelerator in the US. It's the only university blockchain accelerator to offer student fellows programs, which is really awesome for the students to really get involved and actually run a lot of the administrative duties of the accelerator. And it's really awesome because it's a non-dilutive accelerator. And so just by joining the accelerator, you're not giving up stake in your company, because we really do want to prioritize bringing benefit to you rather than doing it for profit. To talk a little bit more about the course structure itself, we're going to be meeting every Thursday from 6 to 7:30 p.m., going from September 17th to December 3rd. The one exception is we're going to take a break off right around Thanksgiving time, but we'll keep you guys updated via email. We definitely encourage you guys to ask questions and start discussions in our Facebook group. During the live lecture, you're more than welcome to ask questions during the webinar as well. And every webinar will be about an hour and a half, but we're going to take breaks throughout because we want a chance for you guys to ask questions, engage with us, and then we'll have plenty of time for Q&A at the end as well. And then we're also going to have weekly guest talks with industry leaders. And so those are going to happen every Tuesday from 6 to 7:30 p.m. Next week, we're going to be kicking it off with the first one. Andrew's going to be hosting Gloria Zhao, who is the former president of Blockchain at Berkeley before me. And she's now doing amazing work in the Bitcoin community as a Bitcoin Core contributor. Some of the goals for this course is, so this course has been in the running for about 2 or 3 years now. And really what we want you to take out of it is a granular understanding of Bitcoin. So knowing it more than just as a buzzword, but understanding how Bitcoin works, the motivations behind it, and the things that have spun off from the ideological beliefs behind Bitcoin. The ability to reason with unfamiliar technologies. So blockchain, is this really technical, fancy term that many people have trouble wrapping their head around. And so we want to break down those concepts so that they're easily digestible for you. Familiarity with trends and notable projects in the industry. This one's really important because at the end of the day, we want this to be more than just an academic lecture, but we want it to be an opportunity for you to understand where the theory that we talk about relates to the applicability in the industry and why these principles are so important. And then the confidence to pursue opportunities for contribution. At the end of the day, this blockchain space, like many technology spaces, are really focused on open source work and open source contributions. That's one of the largest motivations behind Blockchain at Berkeley, is to just have a space for contributions to the space. And so we highly encourage you to take our learnings and build on top of them by going on to do bigger and better things in the blockchain space. And then breaking down the course content just a little bit more. We really want to make sure that you understand blockchain via Bitcoin. So understanding, the history, how it works, why it's used, and how it's abused. And then taking it beyond Bitcoin. So having contextual knowledge in distributed systems, understanding the differences between Bitcoin and Ethereum, and scalability, and some of the considerations that new protocols are having to consider as they create new protocols and as they build on top of existing protocols. And then we're also going to have a guest lecture focusing on DeFi at the end of the webinar series from our accelerator team. And so it'll be a great opportunity to both learn about what's really exciting for a lot of people in the blockchain space right now, as well as to understand more about the accelerator from that team and how you can get involved. And now I want to take just a second for any questions. I see a lot of messages in the chat, and so I just want to take a second to take in that advice.
Also, I'll just take a quick second to say here, when we do these question sections, please feel free to use the Q&A feature rather than just the chat box. It'll help us stay a little bit more organized.
Mm-hmm. Perfect. Thank you, Andrew. Awesome. And yes, we will make the slides available after lecture, as well as having a recording available after lecture. Perfect. So we'll go ahead and dive in now.
All righty. So we're going to start by, we'll just break down what is Bitcoin, right? At a high level, before we get into anything technical, anything of that sort. And so we want to start by addressing a couple of words, a couple of definitions you might have heard been thrown around, and just give you our perspective, right? So 2 words you've almost definitely heard at this point are cryptocurrency and blockchain. And it's easy to conflate the two or use wishy-washy definitions that feel like they apply. It's basically very easy to get confused and to get into arguments with people in the space when you're really talking about the same thing. So that said, like, these definitions are not concrete. It's more like our general view. It should really fall upon you to understand how we look at what a cryptocurrency is and what a blockchain is, and sort of create your own intuition for it, create your own definitions as you learn more about the space. But for a quick snapshot, for us, a cryptocurrency is really any form of currency that's stored completely digitally. So there's no physical counterpart to it, not like a paper dollar backed by gold or anything like that. And it's not issued by a central authority. So there's no Fed or no central bank that's setting monetary policy and deciding how much supply of the currency there is, nothing like that. Which might beg the question, well, if there's not a central authority sort of like making sure that the currency is being used correctly and is being managed, then how do we make sure that it's secure and that it's not being abused? Well, this is where technology really comes in. The crypto part of cryptocurrency is that we secure these currencies using cryptography, distributed consensus, and other knowledge from the space of distributed systems, and some economics and game theory. A big part of cryptocurrencies is actually aligning incentives of the different users so that it helps the system as a whole. So Bitcoin, for example, is a cryptocurrency. And now a blockchain, sort of taken a step aside from the general concept of cryptocurrencies, a blockchain is like it's a data structure that's used to represent a cryptocurrency. So to anyone in the audience who's not from a computer science background and the word data structure means very little to you, you can basically think about a blockchain for now as a database with a very specific format. And so the key point here is that in a blockchain, you're able to store data in a way that like multiple parties can access it without any one party having to lay trust into any other party in order to receive that data. And we'll break that down a little bit more and show you how that's different from the systems we use today. So, let's talk about some key characteristics of a currency. If we claim that we can make a currency out of ones and zeros, we should be able to back that claim up. So what do you need to make a currency? Well, if you search online, there's a couple of different ways that this might be approached. There's like the 4 functions of money, the 6 characteristics of a currency, but these are generally accepted to be necessary characteristics of a currency. So the first is durability, right? Currency can't just break apart or lose value on its own. It's like when I have $1, it should always be worth $1. Another big, big factor to consider is portability, right? I've got to be able to transport a currency from place to place. Otherwise, it's not really usable, right? If I can't bring my money to Starbucks on the corner to buy a coffee, is my money really any good to me? So we've also got divisibility, which is essentially just like denominations must exist. There's got to be like enough denominations to the currency that it's usable, that you can transact and exchange with people, and you're not always confined to like trading in quantities of like $100 bills, right? That's not convenient. Uniformity is very important, or sometimes called fungibility. We'll touch on this in more detail later, which is just that like all units, all base units of the currency have to be identical in value. There can't be anything that distinguishes $1 from another that might make the first dollar more valuable or much less valuable, sort of across the market. Limited supply is important. Mainly like the supply can't just be like arbitrarily pumped up by any random person. A great example here is like, what if we were to use cows as currency, right? They have some intrinsic value. The issue here is that all the farmers in the world would basically just like breed as many cows as they possibly could and artificially inflate the supply of the currency. And this has this basically means it's very difficult to control the price. And finally, acceptability. This is like a very vague one, but just generally the currency must be accepted in a large number of places. Otherwise, it's not really worth anything to you. Like let's say, you come from a village where you trade with seashells. I'm sure we've all heard that example of a barter economy. And maybe that worked great for you in that village and you could buy, all the produce or, whatever you would need. But if you come to, let's say, New York City and you start trying to buy a dollar slice with a couple of seashells, it's not going to get accepted and it's not really going to be considered currency in that context either. And so we'll touch back on these characteristics once we've learned a bit more about Bitcoin and show why Bitcoin actually fulfills these. And so moving on, what are the key characteristics of a blockchain? We're sort of understanding the currency part of cryptocurrency. Like here's the characteristics that need to be checked off. But now the crypto part, like we say we use this blockchain thing, but I just likened it to a database. There are tons of different types of databases. So what is the sort of unifying characteristics of different blockchains? Well, it's three big ones that we feel are the most important. And these are pretty abstract concepts. So if you feel that like this doesn't really clear too much up for you, don't worry. We'll definitely dive deeper into each of these points as the series goes on. But the first of these 3 points is decentralized control, right? So let's compare to a normal database. Typically a normal database, it just gets updated by whoever owns it. There is this notion of an owner in a database. That's not the case in a blockchain. Here we use the consensus among the community rather than just letting one party decide what parties and what other actors are allowed to access, so just see what's on the blockchain and also update it. So now like anyone who wants to interact with a blockchain is able to access or update it, or at least has the permissions to, as opposed to just like, Facebook, you can update your database, like you can update my user record in your database, but I'll never get to touch it. The next big characteristic is tamper evidence. This is pretty straightforward. It's just like if you have put data on the blockchain, it will be immediately obvious to you if it's been tampered with by someone who is not authorized to do so, basically. And often you'll hear that blockchains are described as being immutable, which namely like they cannot be changed. Any data that is in them is there forever. We like to emphasize that this is not exactly true. It's a nice word to be able to drive a pitch with, but more so it is the case that blockchains are tamper evident. I will be able to see if any data has been mutated, and as such I can take any follow-up measures that I might need to change the data back to how I had it set, back to how it should be. But that change still needs to be executed, or the tampering still needs to be recognized. It's not that a blockchain is just immutable, unchangeable by default. And the last characteristic is, well, we call it Nakamoto consensus. This might mean nothing to you right now, which is fine. But basically it just means that, in any database, there's a certain process that has to take place that basically says like, will allow this update to happen to the database or not. You've just created an account on Facebook. Facebook does do some checking of like, oh, okay, is this a real email? Does this account not already exist? X, Y, and Z looks good. Okay, we'll update the database. So now that whole process, when you want to like trigger an update to what's stored on a blockchain, you have to spend some resources to do that. You basically have to put something at stake. And we call this Nakamoto consensus as opposed to general consensus. We'll talk more about what consensus is in this very lecture, but just know that like you have to spend resources to influence the data that is stored. And I know I've tossed around centralization and decentralization as like concepts, as words in the past couple of slides. And these can mean very different things in very different contexts. So we just want to address like how we might be using these terms. And just like before we get into this, centralization and decentralization are high-level abstract concepts. We don't mean to define them in any very technical way that is specific to blockchain technology. There are many ways that a system might be centralized. It could be like politically centralized, geographically centralized. So we do consider this as a high-level idea and not any sort of concrete definition. But here's sort of the vein in which we think about centralization. Sort of the big flags for us of a centralized system is one in which authorization is handled by a single party. So roles and permissions are decided by one single party. Person X can do A, person Y can do B, and I'm the one who says so. And also a big, characteristic of a centralized system is when data, like any data relevant to the system, is stored by a single party. And I'm sure this must sound familiar. Let's take, for example, a bank, right? Your account balance and the history of your transactions, all of that is handled by the bank. You don't have to like keep your own records. I mean, by all means you can, but you don't have to. So if you want to think analogously or in terms of examples, like what else might be a centralized system, think, for example, client-server networking, where when I want to get a website, I have to go to the exact server pretty much that stores that website and have that one place like bring the data to me. Or you could think of a hierarchical org chart where, all executive power, all decisions essentially bubble up to like one party, one position that has this sort of like say-all power. You could think of like political dynasties, right? This is like a very similar to a hierarchical org chart where, we've just had like the same one party, the same family in power over and over, right? Central banks, right? Figureheads. These are things that should pop into your head when you think centralization. I'm sure at a high level, you get the idea right now. So what are some pros and cons, perhaps specifically in the context of blockchain? So the pros are more or less just in the vein of efficiency. Like that's where centralization comes in. It's very efficient because let's think of a database, right? A centralized database system, you can think of like there's one database and the website, let's say Facebook, owns this database. So this is very efficient because all like user data, we just have to store in this one database. If a user wants to run some sort of program, like interact with Facebook, maybe they want to update their profile, they just have to like send in that update request and it gets processed once in one place, by Facebook. It only has to get approved the one time. And then boom, the update is reflected across the whole system. Similarly, in general, like software updates and not just data updates, if that makes sense, are much easier. Like Facebook can update itself as an app and basically force all of its users to adopt the update, which is a model that we're very used to. We're very used to just like click an update when an app tells us that we should. And this is like super efficient on Facebook's end too, because it just needs to sort of code up an update, get it approved internally, and force it onto all of its users. It's very efficient. But the cons here are that there's a lack of sovereignty. Like you lose some amount of control and ownership over your participation in the network, right? This central party can choose to use your data arbitrarily, and you know, of course there's like terms and conditions and there's like GDPR laws that have been put in place, but at the end of the day, like you're not in control of your data. You are not storing it on your computer and you don't really know what's being done with it. And now we know like Facebook sells all of our user profile data to advertisers and whatnot. So this is just sort of like something you subscribe to when you become a participant in a centralized system. And another con here is that there's one point of failure, right? If there's a hack or attack or a server goes down, it really only has to happen once in that one like managing station that, you know, oversees the whole system. Like just the one server has to go down and all of the users are now not going to be able to use Facebook. That's not very resilient. Now, of course, there's like security measures in place to alleviate the issues of fault tolerance, which is a term that we'll be using later, but like basically alleviating the issues of we only have to fail in one place, but it can only do so much. So now let's take a look at, you know, an opposite paradigm, decentralization. So it's more or less the inverse image of what we've been talking about. So here you can think like authorization, like permissions and rules are decided by like a well-known protocol across the whole system. Just to give an example off the top of my head, let's say you're at the mall in the food court and you get online, right? This is a very wacky example, but basically there's no one at the behind the counter or at this restaurant who's going to be telling you like, okay, you go to the front of the line, you go to like the third spot in the line, you like get on the second line, you're just getting a soda today. Like no one's doing that, right? You're like what permissions you're allowed to have and what actions you're allowed to take, they're just like openly known. They're specifically written out somewhere. So in our restaurant example, everyone sort of knows that you just get behind the last person in line. That's fair. That's the protocol and everyone knows to do it. And so this is something you'll see in decentralized systems as well, right? It's like there's just sort of like a protocol, understood way of doing things that is specifically documented somewhere, but isn't like set by any one party. And we'll talk about how like changes to these protocols are organized, but basically you need like a communal vote. And another characteristic, of course, is that data now, rather than being stored by one party, for example, on one server, is stored by all of the participants. And this is might be a little unusual to wrap your head around. You can think about it, and this is called peer-to-peer networking. You can think about it this way. Let's say you want to go to YouTube, right? So how that usually works is you type in like youtube.com, and what'll happen is you send a request to YouTube servers saying like, hey, bring me this video. And YouTube servers say, yeah, I got you. You know, we're storing this video. Here it is. Now in a peer-to-peer networked system, how that might work is you put out a request to maybe a couple of other computers that you know, like, hey, Liam, you know, you watch a lot of the same YouTube videos that I do. Would you happen to know where to find this video? And you just sort of broadcast to everyone that you're connected to, like, hey, I'm looking for this video. And someone will perk up basically and say, like, yeah, I got it, and send it over to you. So rather than going to like, this is the one place where I get my YouTube videos, it's more like, hey, can anyone in the network bring me a YouTube video? And that's how data is stored, right? So you can think, if you want to, you think about this analogously again, this is peer-to-peer networking as opposed to a client-server model. So more about one-on-one interactions. You could think of a flat org chart as opposed to a hierarchical one where executive power is like very evenly distributed across an organization. Everyone has a lot of like decision-making ability. No one trumps everyone else. You could think of like a pure democracy too, where, I mean, this is like the purest democracy is like very decentralized because it means literally every single citizen has the same amount of voting power. So there is no centralization of political power there. You could also think of a barter economy. I sort of like this because it keeps the focus on the one-on-one interactions that decentralized systems are typically centered around. So as opposed to say, you know, a capitalist economy where, you know, you go to your Starbucks, you know, on the corner, you love Starbucks. They're a brand that is very well known. You pay them the money bubbles up to like, you know, whatever parent company Starbucks is a part of, whatever like mega conglomerate. And so at the end of the day, like, your choice of economy, like your different commercial options, are still somewhat centralized because there are like large conglomerates at the top of the corporate world that have a lot of executive power across like all of our commercial choices. Now compare this to a barter economy where it's like, hey, I found like an individual vendor, like an artisan who produces, you know, something that I like. Let me just like find them and have this one-on-one transaction and just like get, you know, this handmade chair or something, as opposed to, you know, going to like a well-known corporation and sort of like feeding into their whole cash flow. And as opposed to in a centralized system where I said you could think of like a figurehead as sort of the representative of a system here, the representative of a decentralized system is its community as a whole. So decisions that are made, if there's like rules that need to be set or changed, it's not a figurehead that does this, but like communal decision making. So again, that might have been like very abstract and very strange. Like, why do we just spend these slides talking about that? But just sort of planting those seeds in your head will really help you understand how we use the word centralization, decentralization as we go on. And just to wrap it up, like some quick pros and cons here, it's essentially like the exact flip of what we were talking about with centralization. So the pros here are that now you have sovereignty and control over your data and your participation in the network. Because data is used according to like an openly known protocol. So you'll know if it's going to be abused. And also like it's on you to store your data or ask other nodes, basically participants in the network to store your data for you. So you have more control over where and how it's stored. And if you want it removed, that's easier to do as well. And also these systems are more fault tolerant, or this is like the opposite of that. A failure only has to happen in one spot case that we saw with decentralization. We're now like, you know, let's say, taking the YouTube example, let's say YouTube servers go down. What are we going to do? We're just not going to watch videos because no one else has the videos stored. But in a decentralized version of YouTube, there would probably be like, you know, a dozen or so computers that store any one video just because they like randomly decided to do so. So now let's say you want to find a video and that one like computer that you always connect with to get that video from, let's say that computer went down, no worries. You'll find someone else on the network to procure the data for you. So it's much more resilient to failure, hacks, and attacks in this way. And the cons are pretty much, you know, what were the pros in a centralized case. This is very inefficient because, you know, all these machines need to store data locally rather than just letting one server do it. So there's basically copies of data across the network everywhere. And in the case where, for example, you need to do some amount of computation if you need to run a program, you know, I was using previously the example of reaching out to Facebook and asking them to run an update on your user info. In a centralized system, that's all you do. You just reach out to the one party, say like, run this program for me, and they do it. But now when we're in a decentralized system, usually or pretty much necessarily what ends up happening is that these computational tasks are re-executed across the network because different machines, different computers need to either run this calculation on their own to receive the results at all, or run it on their own to verify results that they have seen. We'll get into more details about like in what cases you might see that in a blockchain protocol, but know that it's inefficient. Data is duplicated and programs are run multiple times. And it's also very difficult to update the software itself because similarly to how nodes will store data locally instead of just reaching out to the server for it, they'll also like store the current version of the software locally. So basically think about like now when you go to facebook.com, instead of, you know, you send a request to the server brings you back facebook.com. It's like you've got facebook.com saved locally. And when you spin it up, it'll just like run the software on your computer. So now when Facebook wants to make an update, they need to get everyone on their computers to basically agree to this update and you like load it up locally. Because they can't just force push updates on users and they can't lock you out of the app and say like, oh no, you don't get to use it unless you update it. you don't really get any sort of say over the whole community like that. So you have to hope that a majority of the community will like take your update. So that should hopefully give you some idea, just a little bit of groundwork. You know, what's a cryptocurrency? What is Bitcoin? What is centralization and decentralization? And now that we've got that abstract stuff out of the way, we can talk in like slightly more concrete terms. You know, what is Bitcoin, right? So like we mentioned, Bitcoin's a cryptocurrency. It was created by the anonymous figure Satoshi Nakamoto in 2008. No one knows who they really are. That's obviously hotly contested. But what really made Bitcoin stand out, note that it was not the first attempt at a cryptocurrency. What made it stand out was, firstly and foremost, like at least I think, it was the original use of what we now call a blockchain, that data structure. And this was a very interesting way to solve a very important problem at the time. Namely, there's like some security issues. We'll get into that more in depth in lecture 3, but basically the creation of the blockchain was like a very innovative way to make cryptocurrencies secure. And what Bitcoin was able to do that other cryptocurrencies at the time weren't able to do was truly let itself be like in the hands of the users and usable without having any one central entity there to ensure that it's like not buggy, ensure that updates are going there to, you know, enforce monetary policy. There was no central entity that could do that. And most importantly, the Bitcoin system was still secure without needing a central entity to sort of manage it. And this hadn't been done appropriately before. And as I'm describing this, you know, these thoughts of decentralization that definitely pervade the Bitcoin, or I should say the blockchain space generally, you might pick up on some tinges of almost a like humanitarian motivations there. You know, decentralization, no one party in power, you know, very grassroots feel here. And, you know, if you're picking up that vibe, you're not misguided there. Some of the earliest developers on Bitcoin, and in fact, if you read the sort of message that was included with the first ever mined Bitcoin, I'm probably going to get called out on this because I don't think I have it exactly right, but I think it was quoting like an article in like the UK Times or some British newspaper that was slamming the government for, I think, pumping money into the ecosystem and inflating the pound. So you can tell that there is definitely some low-key like libertarian ideologies in the blockchain movement. And it's true, there was a group, I forget, I think I want to say in like the 70s and the 80s and 90s. We'll learn a bit more about them next lecture. This group is called the Cypherpunks, and it was really a movement focused on privacy and the right for self-governance in a digital society using cryptography. Their whole like modus operandi is that in a digital society, privacy is a necessary right, else your data will essentially be used against you in ways you don't know. How do we get privacy? We need cryptography. And so they figured like one very important form of privacy was transactional privacy. Like, you know, I need to be able to use my money without someone looking over my shoulder every time I spend it. So they were heavy proponents of Bitcoin as it was being created. And Bitcoin definitely takes from that ideology as well. And you might notice that, or you might not be surprised to know that those who were early adopters and proponents of Bitcoin were not very trustful of banks, because this is a perfect case of centralization in the current financial system, right? And we actually lay a lot of trust into banks nowadays. We trust them with transferring and redeeming money. Seems like the most basic function of money, but it's very important. And we can't always trust banks to do this. You know, for example, in 2008, during the recession, people were trying to withdraw their money from banks and were just simply unable to, right? The banks didn't have enough liquid money. Same thing happened in the Great Depression in the 30s. So just being able to redeem your money, not something we can always trust the banks to do. Similarly, we entrust banks with personal information that they need to store securely. They have to do that. And there's been cases of you know, breaches and hacks into banks leaking personal information that can then be exposed to, you know, take advantage of these people more. And of course, there's also the accurate recording of your account history, your transactions and whatnot. Like if the bank misrecords that and you need that information for an audit or for your own purposes, well, there's nothing you can really do because it was only the bank that had this info. So, you know, like we had found, it's very efficient when we just have one central party in charge of all this, but we might not always want to put that amount of trust in a central party. So how do we make a decentralized system do everything that the bank does, namely these services? And so that's what we'll be getting into over the course of the rest of the lecture by explaining the different components of Bitcoin at a very high level. You know, there's tons of ways that you can break down Bitcoin into different functional units. At least for the purposes of this lecture, we break it down in the following ways. So there's like the identity system. You know, what is an account in Bitcoin? What is a person, an entity? There's the handling of transactions. So how does one actually send and receive Bitcoin? What does a transaction look like? What goes into it? There's also like record keeping on a distributed ledger. So it's just a simple matter of recording all the transactions that happened, except as opposed to, you know, a normal ledger where you might think like the bank, I mean, for the purpose of this example, you could literally imagine like the bank has a literal paper ledger where they write down all of your transactions. Now imagine like we had to take that one ledger notebook and split it across, you know, a whole bunch of people, decentralize it, right? So that's what a distributed ledger is. We'll be talking a bit about how that works and why it's important. And finally, trustless consensus. So basically like how do we agree on what changes should get made to the ledger? And again, how do we agree on these changes without having to trust anyone? You know, if someone just says like, you know, trust me, I just got 5,000 Bitcoin from so-and-so, you know, we don't really want to have to just trust them, right? But we'll be getting into all of that. So if anyone has any questions on the past few slides here, why don't you drop them in the Q&A? Let me take a look. If I can pull up the Q&A. All right, so we've got a question from SS here. Is openly known protocol unique to decentralization? Sounds like centralization could also use an openly known protocol. Am I missing something? No, you're not missing something. So, you know, centralized systems also rely on protocols technically all the time. As a basic example, you know, any centralized database system relies on HTTP. That's like a protocol for transferring data across the internet. But the difference here, SS, is that in decentralized systems, we only rely on a protocol to tell us everything we need to know about how to interact with the system and how to like execute actions across it. So the difference between centralized and decentralized systems here is that centralized systems might have like a protocol that they use and also custom rules and authorization that are not visible to average users. And one other question, and then we'll move on. So are banks doing anything right now to address centralization concerns and become more decentralized? You know, that's a good question, Christopher. So there are a couple of use cases, you know, in the blockchain industry that banks are trying to fit to that you might argue make them more decentralized. And we'll talk about those. That's things like XRP, but I would say at a high level and it's sort of like a snapshot of all banks in general, no, they're not doing much to address centralization because at the end of the day, it's kind of better for them. They trust themselves to handle everything properly. You know, they've been doing so rather successfully and that's why they have customers. So if they could just own like more of the world's banking customers and serve more people in the world, it's really just like more money for the bank, right? So they don't really need to pursue decentralization because it's kind of like giving up their power. Yeah, there's a lot of interesting like power struggles in organizations that are started in the blockchain space. Okay, but with that, if you have any other questions, drop them, we'll answer them in chat, but we'll move on.
Awesome. Thank you so much, Andrew. And so as Andrew mentioned, Bitcoin is this one protocol that's made up of a bunch of different components. And so now we want to break down those components for you so that you understand, where decentralization and centralization actually make a difference when looking at these protocols and these ecosystems. So first, we ask ourselves, what makes an identity yours? People oftentimes think that an identity is just strictly associated with like a driver's license or a passport. And although that definitely is your identity, really what we break down identity to is just a unique identifier that identifies you. And so what's really cool about Bitcoin is it is how it uses identities in Bitcoin. And so when we think about it and actually break down this ecosystem of all these actors in the Bitcoin network, we don't necessarily know the names behind these accounts, but they do still have an identity because they have a unique address that's associated with them. And so that address, it carries with them through their lineage of whether they're sending it to their friend or buying something. And so we call this pseudonymous. And this is how the identity system works at a very high level in Bitcoin. But we want to break that down a little bit more so that you understand what that long string of numbers is actually all about. And so when we think about going back to like centralization, and identity in currencies, we think about, okay, what is the role of identity in the context of currencies? And so as Andrew mentioned, whether you're sending or receiving money, you have to have an identity so that somebody knows where to send it to. Same with claiming money, but then also for blame. And so we want to be able to know which account spent how much money, and we want to be able to agree on what has happened in the past and to be able to prove that a certain amount did something. And so we want to be able to know how are the actors in this ecosystem actually interacting with each other. And so also when we think about identity, it's really important because it helps us to make sure that no one party can intercept, modify, or tamper with somebody else's transaction, especially since this is a decentralized system. Everyone is involved in the settlement of these payments. And we also want to think about authentication because we don't want anyone else receiving, claiming, or spending your money. And so for your protection, currencies require authorization or authentication to ensure that you and you alone have control of your assets. And so when we think about identity in daily life, even outside of a world of cryptocurrencies and currency in general, one great example is houses and mailbox keys. And so houses have an address. That address is the identity of the house. So I can easily plug that into Google Maps and see where I'm going. I can verify that when I pull up that is the house, in fact, that I want to arrive to. But then it has a mailbox and a mailbox key, right? And so if I'm delivering mail to that house, then I can easily slip in a letter into that mailbox. And so therefore I am sending that mail to the house, but I can't open up that mailbox again and take the money out, right? And so that's where the key comes in. Or we can think of it like emails. And so emails have aliases or, liam@berkeley.edu as an example, and then passwords to access the inbox. And so anybody can create an alias. Anyone can create an email. Anyone can send an email to anyone else that also has an email. But only the person that owns that email address is able to access the inbox and see who has sent them emails. And that's using the password. And so when we relate that to Bitcoin, Bitcoin is very similar in that it has public and private keys. And so public keys, just like the name implies, are public and open. And so that's the unique identifier for every identity and every individual in this network. And then the private key is private, right? And so that's what you really want to keep secret, as that's going to unlock your wallet so that you can spend money and access the money that has been sent to you. And so how does it work with identity in financial systems, right? You go to the bank and you basically confirm your account by using your personal information, like your social security number, birth date, address, ID, etc. And then the bank basically makes sure that all usernames are unique. And so this management happens all within a centralized system. And so what we want to be able to do is have a system that abstracts a lot of this away so that we're not relying on that centralized party in order to ensure people's identity and limit who can and who can't use the service. And so going back to the example of a mailbox, each identity is represented with this unique public key. And so these corresponding private keys act as your key to unlock the public key and therefore access your money. And so unique private keys are generated randomly, and then the public keys are derived from your private key. And so it's really easy. Anyone can go online and easily generate these private keys, and then automatically they have a public key associated with that private key. And so again, just to reiterate, the public key is for receiving, whereas the private key is for redeeming. And so a few things to note. For one, no personal information is required. And so many people ask, does this mean that Bitcoin is anonymous? Short answer is no. Bitcoin is not anonymous because that public key is still associated with the user for every transaction that they spend or receive. And so because of that, we call it pseudonymous, because we don't necessarily know the true identity behind the public key, but we are still able to track their identity nonetheless. Another consideration is that there is no limits on how many accounts you can make. And so many people ask, does this affect the security of Bitcoin? And we're going to touch on this in the next slide, but essentially consensus ensures that actors cannot overtake the network simply by creating multiple identities. In addition, it doesn't affect the network or the security as well because because there's almost a near infinite amount of private keys. And so that brings us to the next point, that there are no restrictions on the amount of keys that can be taken. So for example, if I wanted to go to a Bitcoin wallet online, then I could easily generate a private and public key, and then I could refresh the page and create another private and public key. And I could keep doing that all day long, and it wouldn't affect the network, because at the end of the day, there's a ton of possible combinations. And so, you know, this is the first time we're seeing a black slide. So I just want to give a quick caveat that the black slides throughout this entire series are going to be a little bit more technical in nature. So if it's going over your head, don't worry too much. But this slide in particular is just to demonstrate just how hard it is to overlap private keys. And so I'm not even going to try and say the number on the screen, but there is a when I say that there's a near infinite amount of possibilities, that specific number is 2 to the 160th power. And so to put that in scale, the population of the world is right about 7.8 billion people. And so every single person would have to have about 2 to the 126 addresses all to themselves. And then every single person would have to do that in order for the chance for duplication to occur. So like we said, it's very secure with this identity system. And so I know these are very new concepts, and so I just want to take a second. If people want to stretch their legs, go for it. But otherwise, if anyone have any questions for how these public keys and private keys work and why they're so important to the network, please feel free to ask.
Yeah, Liam, I saw one question I would just like to hear your take on as well. It's a bit tangential, but I know you have some relevant experience here. Luis Tapia asked, what is Ripple XRP? Is XRP decentralized?
Yes. So great question. So Andrew touched on it very briefly for the question in regards to how are banks working with decentralization. So Ripple is a company, XRP is a currency. Those two are independent of each other. But Ripple works with the XRP currency to enable banks for cross-border payments. And so what's really cool is that Ripple uses a product called RippleNet and on-demand liquidity that allows for banks to instantly be able to convert USD into XRP and then XRP into another fiat currency. So we can talk about francs or pesos. And so by having that conversion just being simply through the conversion of fiat to XRP, XRP back to fiat, then they're actually able to reduce cross-border payments down to a fraction of a percent. And so really, really cool products that are using that enabled technology. One question I see is, if you lose your private key and forget it, how, if at all, can you get it back? This is a great question. And so this is sometimes considered one of the flaws of cryptocurrency, is that there's no centralized party to be able to give you like a forgot password prompt. And so it's really, really important that if you do use cryptocurrencies, that you do not lose your private key, because once you lose it, there is no way to kind of forget your password and reclaim access to that wallet. And then I'll answer one more question here. If the public key is derived from the private key, is there no way for people to reverse engineer that? Not sure if I heard that correctly. So great question, Farzad. And so, yes, you did hear that correctly. The public key is derived from the private key, and it uses some really fancy cryptography terms, specifically elliptic graph curve, to be able to create that, that key match. And so what's really cool about the cryptography behind it is that it makes sure that people can't reverse engineer it. But it's a great question. Awesome. And now I'll pass it back over to Andrew to tell you a little bit about transactions.
Sweet, thank you. Alrighty, yeah, let's talk transactions. So the sort of motivating question for this section is, what makes a transaction valid, right? It's not really something that we ever had to concern ourselves with as users of money, because it was never our job to check if transactions are valid. The bank just does it. Well, let's put ourselves in that headspace. You know, what might one need? And so we believe that, like, at the most basic level, you need these three things, right? Proof of ownership. And this is talking about ownership of the money in the transaction. So you have to be able to prove that that money belongs to you, right? You have to have enough money. And you also have to be able to show that there are no other transactions using the same money, right? And so this third point might seem redundant. It might seem that, okay, well, look, if I have available funds, that means those funds weren't used in any other transactions, right? Like we can just leave it at that. And we actually have to be a little bit more careful, you know, maybe just at a bank where they would probably just use like a balance sheet and subtract and add to your balance to like record what money you have. For them, it might just be enough to check like, okay, is the balance greater than how much they're trying to send? Cool, that means they have available funds, and clearly since they like have some amount in their balance, those funds haven't been used elsewhere. But Bitcoin does it a little bit differently, where Bitcoin will literally track like each unit of Bitcoin and where and how it's used. So imagine, rather than the bank just saying like, oh, Andrew spent $50, let's subtract it from his account. It'd be more like, okay, Andrew spent these $51 bills, or he claims to have spent them. And yeah, like maybe those $51 bills were in his account at some point, but let me just make sure and check those serial numbers and make sure he didn't use those same $1 bills somewhere else. And we'll talk about like why we want to, you know, check that exact condition to prevent something called a double spend attack. We'll explain that in more detail. And so you'll see why this third point is important. So like I was just sort of talking, in the traditional model, or in like a sort of simplified banker's model of, you know, how are transactions tracked, you might do it like this. You might have some central manager, it's like some basically accountant or database admin, that would keep track of all the account balances and verify that transactions are valid. Or I should say, like, you basically have like a program running in one place that would do this, but you get the idea. So each account would have some available balance, just like some total. When they spend, money is subtracted from the total. When they receive, money is added to the total. And pretty much the only verification that needs to happen was like, are they trying to spend more money than they have? Don't let them do that. And, you know, is it really them spending this money? Like, is their account not getting hacked? Which is basically just like that job falls on like customer support. And that's mostly just issues with like how credit cards are handed out. But point is like, you don't really track the individual units of currency. You just have like an account total and you add and subtract from it. And this works really well. I just realized you guys can't really see what's going on here. Wrong way. But you get the idea. There's money happening. And this works really well. It's really efficient. I don't have to track every single dollar bill. When there is just like one central place that needs to verify everything, and they can like make sure that all the transactions basically come in one specific order, this will work, but it won't always work. So what does Bitcoin do to represent transactions? Well, they don't just use balances and adding and subtracting from them. They use something called the UTXO model, where each account holds a set of unspent transaction outputs, or UTXOs, which we like to think of them as little piggy banks. So a UTXO is an arbitrary like amount of Bitcoin that is like owned by you. Well, let's use the case of Alice as in the example here. So Alice owns these piggy banks, these arbitrary like quantities of Bitcoin that she has yet to spend. So as opposed to like you own some number of dollars or dollar bills and it's like that is the unit, it's $1. Here it's like you own some number of piggy banks and these piggy banks have like any quantity of Bitcoin in them. And so a UTXO, it can only be used once, and it has to get spent in its entirety. And this is where the piggy bank analogy like really helps out, because you can think about whenever you want to use money, whenever you want to use Bitcoin, you have to break open a piggy bank. So that's enforcing the fact that it's both used only once and it's spent in its entirety. And you know, that might make you ask like, okay, so like, if I have to spend like, if I have to break open these piggy banks and use all the Bitcoin I have in them, you know, how am I going to get exact change? You know, what if if it just doesn't add up? So let's just walk through like a basic transaction, what that might look like. So let's say we've got Alice and Bob here, right? And Bob remembers, oh, Alice, you still owe me 2 Bitcoin for that coffee last week. Because, you know, coffee obviously costs somewhere around 24K. So Alice, what she'll do is she'll pluck those 2 specific piggy banks out of her account. So in this case, she's got to transfer 2 Bitcoin to Bob. And we saw that she has these piggy banks valued at 1 and 1.2 Bitcoin. So what she'll do is just pass those piggy banks into a transaction. You can think of like you can think of this as like taking a piece of paper, writing like, this is a transaction of Bob. I'm using like piggy bank ID 1 and piggy bank ID 2. And then as a result of this transaction, we will create a new piggy bank ID 3, that is owned by Bob with exactly 2.0 Bitcoin inside of it. And then you might ask, like, oh, well, look, the sum total that Alice had inputted in terms of UTXOs was 2.2 Bitcoins worth. So what Alice will actually also say is, and this transaction will create another new piggy bank with all of the leftover funds, and I will be the owner of this piggy bank. So she addresses it back to herself. But notice that like piggy banks with IDs 1 and 2 are forever destroyed as a result of this transaction. So let's go over our conditions for validity again. So how do we have proof of ownership? So you have to prove that you own one of these piggy banks. Well, this is where public and private keys come in again. You can do something called generating a signature with a private key, which you don't need to know the specifics of, but essentially what it's doing is like saying, you could think of it as putting a thumbprint, right? Right on that piggy bank. It's saying like, look, this definitely belongs to me, and you can verify that because you can check that this thumbprint belongs to me. So similarly, you can check that this private key belongs to me. But if you're trying to pretend you're me and use my money, you don't have my thumbprint, i.e. you don't have my private key, so you won't actually be able to prove ownership. So we use our private keys to prove ownership of UTXOs. How do we check that there are available funds? Well, UTXOs are going to have to be inputted directly into a transaction. So if in that transaction, it's just like the sum of the values on the right-hand side. So if this 2.0 and this 0.2 doesn't, is greater than the sum of what's inputted, clearly there aren't available funds. And now we can also track that no other transactions are using the same funds. And we'll show you exactly how we like do this verification that, okay, these funds weren't used anywhere else. But now you can at least see that we might have to track it, because now we're not just updating account balances like this. We're actually saying like, look, these piggy banks were used in only this transaction. And I promise that these piggy banks weren't used in any other transaction. So that's how transactions are modeled in Bitcoin. Rather than dollar bills, we've got piggy banks. That's how I like thinking about it. Any questions on this? Let me bring up the Q&A here. All right. So when there are excess funds, where does that go? Back to the original sample. For example, in the transaction, who does the 0.2 go to? Yeah, great question. Sorry if I wasn't clear enough on that, but you hit it right on the head there. When there are excess funds, the originator of the transaction will address them back to themselves. So in this case, Alice, this excess 0.2, Alice just addresses it back to herself. So basically the outputs of this transaction say one piggy bank owned by Bob with a value of 2, and another piggy bank owned by Alice with a value of 0.2, or like i.e. the change. Cool, cool. Okay, a couple other questions. I'll just answer one more and then I'll hand it off to Liam and answer the last one in chat. So are UTXOs constantly being created and destroyed? Like total Bitcoins are the same, just how they're distributed is changing? Oh, great question. Yes, so anonymous attendee, yeah, that's exactly how it works. All the time, UTXOs are constantly being created and destroyed, but the total value of money in the system, just as a result of transacting the way I've shown you so far, will not change. It's rather that like now this money was once in a piggy bank owned by Alice, it's now in a piggy bank owned by Bob, but the total supply will not change. It's basically just the ownership. All right, and I'll hand it off to Liam now to continue.
Awesome. Thank you so much, Andrew. Yeah, and so now we're going to go a little bit deeper into distributed ledger, why it works, how it works, and some of the benefits that we see from it. And yeah, so let's dive in. So when we think about record keeping in a traditional model, we can think of two actors, so Alice and Bob. Alice wants to easily be able to send Bob a few dollars, and so it's very easy for Alice to ask the centralized party for permission to send money. But in a decentralized system, we want Alice to be able to send money to Bob without having to worry about that centralized party. And so, you know, data is secured and updated by this one central party, which creates a choke point. And so if that centralized party ever comes down or ever acts maliciously, or if they just want to follow their own rules and prevent Alice from sending money to Bob, then they're fully able to do that. And so securities, and then there's security measures in place to prevent hackers and failure. And so when we think about centralized systems from a security standpoint, security comes as a secondary. You have to build security into centralized systems in order to make them secure. But we want to figure out how to make it more secure and not so that we don't have to worry about it as a secondary. And so this is where blockchain comes into play for record keeping. And so rather than just having one centralized party, data is stored by it and is updated by everybody in the network. And so we don't just want one person to keep track of the transactions. So we have to have everybody keep track of the transactions. And so there's just a couple people in this network and if we only had a couple people in this network have access to the information, then that still creates this centralized choke point. And so we let everybody in this network have a copy. And so it's transparent and fault tolerant by design because everybody in this blockchain network has to come to agreement in order for a transaction to take place. And so when we actually think about the structure of these blockchains, we want to think about how we're bundling transactions into these blocks. And so if Dan, Alice, and Carol are all sending money to each other, then the transactions are linked to transactions that happened before to ensure that the transactions are valid. And so every single transaction in terms of lineage will point back to the previous transaction to ensure that transactions don't happen out of order. And now you might wonder, why is this important? You know, as I send money, shouldn't it automatically just be processed as we go? But no, because if the reason why we don't want to store every single transaction individually is because that means that every single time a transaction is made, everybody's database, everybody's copy of the blockchain has to be updated at the same time. But it takes time for that information of a transaction to propagate through the system because of latency and other various factors. So we store the aggregate outcome of various transactions in a single block. And so this speeds up the efficiency of how we're actually able to bundle and process these transactions. And so that's why every single block has to point to the previous block to ensure that no transactions are happening out of order. Because if they do happen out of order, then Andrew will showcase in just a few minutes some of the attack vectors that can come out of that system or come out of that problem. And so, you know, this right here is the core of distributed and decentralized systems. And so I just want to take just a few minutes to stop and pause in case anybody has any questions. And so one question from SS is, does this mean that everyone knows how much money everyone else has to make sure that others don't spend more than they have? Yes, exactly. And so what's really cool, and Andrew's going to elaborate on this a little bit more, is we had this problem of double spend attacks. And so, you know, especially because they're bundled in these blocks, in theory, before Bitcoin came about, I used to be able to say, okay, I want to send $5 to Andrew, but I also want to send $5 to my mom, and I only have $5 in my account. And so one problem of previous iterations of cryptocurrencies is that they weren't able to account for this double spending of transactions before the transactions are actually processed by the blockchain network. And so what we're ensuring is that in order for your transaction to be included in a block, that transaction is actually valid and that you have enough balance in your account before you can send it. One question from Raul, how do you reverse transactions? So great question, Raul. In short, you can't. If the blockchain is continuously moving forward like it should, then there is no way for you to reverse a transaction. And so that's what ensures the security of this system. Because whereas you have a normal centralized party that could ensure the reverse the transaction, we're removing that centralized party because maybe we don't want people to have the ability to reverse our transaction. Now, there is a caveat to that answer, because what we could do is if everybody in the network came to agreement that we all wanted to reverse a transaction, then as an entire network, we could decide to change the local copy of our databases, but we would still have to come to consensus for that change to be made. And to date, there's very few instances where blockchain networks have come to that consensus. What is a seed phrase? Great question, Ashish. So a seed phrase is used to access your crypto wallet. And so seed phrases make it a little bit easier for you to be able to store the password or the private key, because whereas a private key is just a random string of letters and numbers, a seed phrase is a series of words that are able to be computed to that private key to be able to unlock your private key. And then I'll answer one more question here. How does pointing to the previous block help? Can you elaborate? Yeah, so let me go back just a couple slides. Yeah, just one slide here. So the reason why we want to be able to point to the previous blocks is because everybody's constantly working on the next block in this network, right? And so if me and Andrew are both validators or miners in this network, then we're constantly trying to compute these puzzles because we're using proof of work, which is a consensus algorithm that Bitcoin uses, which we'll elaborate more later on. And so we're constantly racing to find this puzzle. And what we want to make sure is that, okay, if Andrew is able to beat me for not the current block that we're trying to figure out, but the next block that would come in the series, then we want to make sure that he doesn't push that block before I push mine. And so it's just really making sure that the transactions are happening in the correct lineage. And now I'm going to go ahead and pass it on to Andrew to talk about trustless consensus.
Alrighty, let's get it. So I know that we're gonna push over time a bit. Excuse us for that, but this is the last like content section, so please bear with us. And this is a really important one. Consensus is all the rage in distributed systems, especially blockchain ones. So let's make it trustless now. So before we get into that, what is consensus? I'm sure that, you audience members have heard the word generally, but it's got like a slightly different meaning in the technical context that we're going to be talking about it in. But again, so at a high level, consensus is just the process by which a network's participants come to, really an agreement on any decision to be made. Typically, we view consensus as the process by which like a network's participants agree on updates to like some central store of data. And that's also the view that we can continue using here because in our case, we're really, we want to find consensus on, which updates do we make to this ledger of transactions. So it is that central piece of data that we need to agree on how to update. And so traditionally, like in the financial use case, or in the use case of currency, consensus is very simple. We leave it all in the hands of the bank. Whenever I want to send money, I basically just tell the bank like, yo, I'm about to send $3 to my boy. And the bank is like, yep, sounds good. I'll add it to the ledger. Or no, you don't have $3, so I won't add it to the ledger. But we basically just like let the bank handle all of the updates to the ledger. We never worry about it as users. But that's not what we do in a decentralized system. It's all about power to the user. So what we're going to do to explain some of the decisions that are made in Bitcoin's consensus algorithm called proof of work is build up a decentralized consensus, not exactly Bitcoin's, but like a simplified version, and expose, what are some of the pitfalls at each like successive level of complexity. So let's start with like very naive consensus, decentralized consensus, right? Where everyone will broadcast every single action that they make, and everyone else will just accept that action is valid and not really dispute, right? So here we've got Alice, Bob, Carol, and Dan, and they're all just sending transactions across the network. Boom, Alice to Bob, Bob to Dan, Dan to Carol, and they're just approving it willy-nilly because that's naive consensus. Just like, okay, cool, transaction approved. Put it in the ledger, right? Now, what's an issue that might arise with this? I'm sure everyone in the audience can think of a way to game the system, right? So here we're going to introduce the double spend attack. The motivational issue with any sort of digital currency is what's stopping me from spending the same piece of currency twice. You can't spend the same dollar twice in real life because you can't just copy paste a dollar. And even if you're a great counterfeiter, like, would you be able to match up the same serial numbers? I don't know. The point is, like, it's very difficult to do with real physical money, but when we're talking about Bitcoin, which is just digital, like, why can't I just like Control C, Control V, send the same Bitcoin? And so this is what Alice is about to do with our naive consensus protocol here. So what Alice does is she basically broadcasts a transaction that says, I just sent this one Bitcoin, or like this UTXO, to Bob. And then she'll broadcast another transaction where she says, look, I'm sending this UTXO, and she uses the same one, like the same ID, and I'm sending it to Carol. And since we're using naive consensus, no one really double checks this. So just like, okay, you're sending Bitcoin to Bob. Cool, looks good to me. Prove it, put it on the ledger. Oh, you're sending Bitcoin to Carol. Cool, looks good to me. Put it on the ledger. But now Alice, if she was buying an iPhone from Carol and then a MacBook from Bob, I mean, she just got one of those for free because she spent the same Bitcoin twice. So what can we do against this? So now let's introduce voting. We'll call this democratic consensus. These aren't like official names, by the way, naive consensus, democratic consensus, it's just like what we decided to call it. But now basically let's just like include the ability to vote, where when you want to like make a transaction, you broadcast it, but now a majority of the network needs to vote in favor of that transaction for it to be put on the ledger. So now when Alice tries the same thing, that first transaction, let's say the first transaction was to Bob. Cool, I send this UTXO to Bob. Looks good to me, says everyone, and the transaction gets put on the ledger. Now she tries her double spend. She says, haha, I'm actually sending that same UTXO to Carol, except now our participants have the ability to vote no on that and be like, no, you're not. We know that you already spent that money. So sucks for Alice, she can no longer double spend, and it looks like we've got a secure financial system. But wait, what if we could just overrule how many votes there are? You know, creating public-private key pairs, so namely creating identities, is very inexpensive on the Bitcoin network. It's inexpensive all the time, unless there's like some special weird way to set them up. But in Bitcoin, it's very easy to make a new identity. So what's stopping Alice from making a bunch of accounts, like shown here, and trying the same double spend attack, but now when Bob, Carol, and Dan try to vote no on her second transaction, she'll just overwhelm the network's votes with her own votes from her own accounts that she controls. And now she's successfully double spent again. And we call this a Sybil attack. A Sybil attack is any attack where you basically like have your way with a network by creating more accounts. So like in any system where like having more identities means more influence, it might be, you know, susceptible to a Sybil attack. But the name doesn't really matter right now. So to protect against Sybil attacks, where you can basically just like put up as many votes as you want, now we're introducing like the concept of Nakamoto consensus, where you've got to spend some resources to put up a vote, okay? So in our case, and in Bitcoin's case actually, this resource is going to be just computational power. You have to like make your computer waste time. So now whenever voters want to like vote on whether a transaction is valid or not, let's make the voters just waste a bunch of time, just do a bunch of pointless brute force computation in a way that's provable. So there's no way to fake it and say like, trust me, I just like, you know, did this puzzle like 40,000 times. It has to be in a way that there is proof. And, you know, we're not going to get into the details of that, but basically the way that we make them do brute force computation, there's no way around it. Actually, you can think about it this way. Like what we have the voters do at a high level is essentially put a blindfold on and throw darts at a dartboard with a very small target until one of the darts makes it in the target. And this way, so we can both prove that they've like done a lot of work, because we would see all of the darts in the dartboard. And we would also be able to very quickly verify that they like actually like finished the job, because we would see the dart in the target circle. So you can think about it that way. They're just chucking darts until they make one. Why does this help us? Well, this helps us because Alice, although she might have been able to create a bunch of fake identities, Alice only has so many computers. At the end of the day, she only has so much money. She's got finite resources. So that means, you know, let's say Alice sends that first transaction to Bob, it gets approved by anyone. Now Alice is trying to send that second transaction to Carol. And so, you know, Bob throws his darts, he puts up a vote. No, I don't trust it. Carol does the same, she puts up a vote. No, I don't trust it. Dan does the same. Alice, so she puts up her own vote, but she still has to use her same computational resources to solve this puzzle, throw those darts for the rest of her accounts. And since she only has limited computational resources, she basically like won't have enough of those resources for all of her accounts to put up a vote in time, more or less. So now that we force our voters to commit some sort of resource, some real life provable resource that there must be a finite amount of, we can sort of ensure that you can't just arbitrarily have like whatever power you want in the network by creating more free accounts. And this is how we prevent double spending and prevent Sybil attacks. And this is pretty similar to Bitcoin's actual consensus algorithm called proof of work. You might get a little more sense out of the title now. And of course, in lecture 3, we'll be talking on a very close level exactly what that algorithm looks like. But this is the high level idea. People have to prove that they did work in order to participate in consensus. So any questions on that? All right. So let's see. Anonymous attendee asks, how can transactions get approved quickly? If consensus takes a long time, can't Alice double spend in the meantime? That's a really good question. I don't know if this is the same anonymous attendee from before, but the anons are popping off. So actually, we want consensus to take a long time, because this way, if it takes us like, well, actually we aim for 10 minutes. We want it to take about 10 minutes for every single block, but you can just think about it this way. We want it to take 10 minutes for every single transaction to get approved. The reason we want that is because people are like spamming the network with transactions all the time. So if we could approve them super quickly, it would actually be really hard to figure out what's the proper ordering of these. So when we make them take a while, there's basically like a higher probability that they will come in and be approved with more time between each approval, so it'll be easier to order the blocks. Now that doesn't really answer your question of like, doesn't this like give someone the opportunity to double spend, right? Like I put transaction 1 up, and while everyone is busy trying to figure out does it work or not, I put transaction 2 up, get a whole different crew of people to figure out if that one works and dupe the network anyway. So the way that we combat that is with something, I mean, we'll talk about it more in lecture 3. It's this notion of confirmations, but it basically means like, I don't actually consider as a user, like let's say Alice, I'm Bob, Alice puts up a transaction that says I get her money. Well, I don't actually consider myself as having that money until I've seen 6 blocks on top of it in the chain, which is basically saying like enough time has passed that there's no way Alice can double spend me at this point. So it's also on the user to wait a bit to make sure that Alice hasn't double spended while consensus was going on the first time. All right, SS asks, is there a time limit to complete the dart throwing? So not exactly, it's more like a race. It's more like, so Alice says that she wants to send Bitcoin to Bob, and she tells everyone in the network about this. And now, we'll talk about this a bit more later, but you're actually incentivized to do the dart throwing. You'll make a little bit of money out of it. So as soon as the network finds out about this transaction, everyone starts throwing these darts. And the first person to throw the dart in the right spot, we just trust whatever they have to say about it. And like we let their validation or not be the final say, which means like once they have finished the dart throwing for that block or for that transaction, it like everyone else's results are just disqualified. Like we don't care if you were throwing darts for that transaction. It's already on the chain. It's done. Go start throwing darts for the next one. So it's more of a race and only one person wins. And then last question I'll answer here. And then we have a quick review section. Does the consensus require everyone to vote? AKA everyone has to vote on every transaction, or is it just a random subset of the network? So it does not require everyone to vote, but you can opt into voting. And while this is computationally expensive, it is also like economically incentivized. It's not that everyone is required to vote, but like a large number of people will take it upon themselves to vote because they can make money at the end of the day. All right, and I'll try to let the rest of these questions get answered by our panelists here. I'm gonna move on into the review section, and we'll try to make this quick, just a nice recap, nice decompress, to wrap things up here. So some quick review. We started off the lecture discussing what is a currency and are we sure that Bitcoin is good enough of a currency, right? Can it fit the bill? So durability, right? Yes, Bitcoin is durable. Once you have that UTXO and it's recorded in your name, that's stored forever on the blockchain. And forever because as long as there exists a community that wants to keep the blockchain around, your data will be on it. It's not like, oh, if the bank servers go down one day, poof, there goes all your money. No, because now we're not just relying on one bank. We've got a whole network of people to keep my ledger intact. Portability, of course it's portable, especially we'll be talking about like, you know, how some of the computational inefficiencies of Bitcoin can be mitigated for like, you know, the ability to use it on the phone, for example. So it is possible to literally have like your entire life savings in your pocket, portable with you everywhere. I mean, this is possible now with like how banks allow us to manage our accounts too, but still true for Bitcoin. It's super divisible. You can trade it in arbitrary quantities of as little as, that's 1 times 10 to the -8 Bitcoin. That unit is called a Satoshi after the creator. But it's very divisible. And it's not like, oh, it's got to be in like a cent, $1, $5, $10. No, it's just like whatever amount you want. It is certainly uniform. There is no distinguishing characteristic between one Bitcoin and any other, or any like fraction of a Bitcoin and any other, that would make it worth more than another in any like domain. So it is like uniform in value. Now there's a slight caveat that is not worth going into here, that actually, depending on how private keys are used and how you manage your own account within Bitcoin, it might be possible to basically figure out who you are based on your public key with enough data from the outside world. And then, like, let's say you're a drug dealer and, 40 transactions down the line, this Bitcoin that you used to own falls in the hand of like a normal user. And now McDonald's is able to say like, no, normal user, I'm not going to take your Bitcoin because I can see its history and see that a drug dealer used it in the past. Technically, that makes that Bitcoin less valuable because now it can't be used in any of these other places, and that'll bring its value down. But we're going to talk more about fungibility and privacy in Bitcoin. And so this issue is actually like tackled and mitigated, and it is still definitely like sufficiently uniform Bitcoin. Like more so I would wager than fiat currency. There is a limited supply. So as opposed to like how, for example, the US Fed handles money, which is just like, okay, we'll set interest rates and that'll like incentivize investment and that'll like affect how much money we print basically. Like that's a little bit more variable and flexible. Here, there's still limited supply, but there's no monetary policy like, oh no, it looks like inflation's really high for Bitcoin, we should stop like minting new Bitcoin. No, it's like very deterministic. It's basically like every like X number of blocks, the rate at which we mint new Bitcoin goes down in half. So you can imagine like over time, Bitcoin starts being like produced at like a very high rate, but it does like asymptotically reach a finite limit of 21 million Bitcoin. There cannot exist more than 21 million Bitcoin. And we haven't hit that cap yet. And finally, acceptability. That's really the sort of the stinger here. Is Bitcoin acceptable? Well, to be honest, myself right now, I would even say probably for the most part, no. Like if I go to Starbucks, they're not going to say like, okay, yeah, you want to pay in like cash, credit, or Bitcoin. They're not going to give you that third option. But hopefully this lecture has given you some understanding for why Bitcoin should be more acceptable than fiat money, because it is more reliable. Now we're not trusting a bank to keep track of like what money I have and ensure that everything is valid and like protect the value of the money. Now we're just trusting algorithms and cryptography and essentially game theory to make sure that the money is used in a secure way and isn't like hacked or modified by any like random malicious third parties. So like from that reliability, from that algorithmic reliability, will stem a stronger feeling of acceptability. So basically we argue, yeah, Bitcoin can totally be a currency. And so just to sum up what we went over in this lecture, so the 4 like main components to sort of like, if you want to think like, what did I learn at that lecture today? So think about these 4 components. This is what Bitcoin is made of, right? Identity. What is my identity? It's a public key and a private key. You can think about it like an email address and a password. How do we keep track of transactions? Well, instead of just like subtracting and adding to some account balance, now we're basically just like handing out actual units of currency. Like actually, you could think about it as like passing cash between one another, except now it's like in piggy banks. You should use the piggy bank analogy. It's actually pretty accurate. Now we've talked about the distributed ledger, which like at a high level just means like we don't store the data in one place. We store the transaction history on everyone across the network. And finally, trustless consensus. Well, so cool, like now that the data isn't stored in one place, how can we be sure that it's being updated securely and appropriately? Well, first of all, we have like everyone in the network validate transactions. So we can actually be sure that they're valid. Like someone has to do that job. And we don't have to trust some random person that they did this job correctly and that they're not lying to us, because we get everyone's eyes on it and we force them to like prove that they actually put the requisite time in. And in doing so, we don't allow malicious actors to just like easily do what they want with the network. And that's pretty much it. I mean, I will definitely leave it open to questions. Hit them in the chat, hit them in the Q&A. I'll stick around to answer them. But at this point, I know we've kept you a bit. So thank you for coming to Fundamentals, Blockchain Fundamentals webinar, Lecture 1. We definitely hope to see you around for many more. Please post in our Facebook group any feedback on today's lecture. If there were some things that were, inefficient, if you think we could have done something smoother, if you saw like a different webinar that presented in this way and it worked really well, anything that you want to mention, please do so in the Facebook group. Let's see. Okay, and then we've got a quick question here from Sasha Toborov. Do humans do the voting, or is it just computers? Yeah, think about it as computers. Honestly, we used voting in this like sort of toy example of consensus. It's not exactly voting in the way you're used to, where you basically cast a tally for one option. But at the end of the day, it's just like programs that are running that do this verification in the exact right way. Just think about it as a computer doing it. It doesn't take human thought. Okay, is it possible to post a list of the questions and answers from this lecture on the LinkedIn page? That's interesting, Ria. We were definitely planning on doing a recap of the questions that were asked and their answers, and this will definitely be on our Facebook page. So again, please check it out. But yeah, we'll discuss, how much cross-posting we want to do on LinkedIn and other networks, but definitely go on the Facebook to stay optimally in touch. Liam,
one question I just want to answer real quickly for Dorothy. It was difficult getting the link. Will it be posted for next time? Yes, Dorothy, I'm so sorry that you guys had difficulty getting the link. That's totally my apologies. And I really appreciate you guys joining us for today. I do want to note that the link is going to be the same for every single one of these fundamental webinar series on Thursdays. The only difference is that there is a different link for the Tuesday session. And so I'm going to go ahead and send that link again on Tuesday before the Tuesday session. But we're also going to do a better job of automating some of that process so that that information is upfront for you guys. And then one question from Isaac. Whoops, never mind. Someone got it. Perfect. And yeah, as Andrew mentioned, thank you all so much for joining us today. We'll stay on for a few more minutes if anyone has any feedback, questions, or concerns. We definitely want to answer them. Apologies also for starting a little bit late today. We're definitely going to be trying to start on time for the future sessions. And we're really excited to have you with us on this journey. This was just designed to be a primer and introduction to this ecosystem. And so now that we've gotten past some of the, high level terms, now we're going to be able to start diving into some more specifics as some of you guys have asked for.